Integration using series. So in this video, we are going to evaluate this integral using the series interpretation of ln of 1 plus x. So we'll just find out how the series interpretation can make the evaluation of integrals a lot easier at times. So we have this integral from 0 to 1 ln of 1 plus x over x dx. This is one of the famous integrals and can be solved by many techniques including Feynman's techniques and more. But in this video we are going to use the most easiest of all, that's by using series. First of all, we know that from the Taylor series expansion of ln of 1 plus x, the series representation is just x minus x squared by 2 plus x cubed by 3 minus x4 by 4 and so on. And for this, the modulus of x should be less than 1. So for this to give a more accurate result, modulus of x should be less than or equals to 1, and that is what we have over here as well. The x ranges from 0 to 1. So we'll use this series. Now we have integral from 0 to 1. This is just x minus x squared by 2 plus x cubed by 3 minus x4 by 4 and so on over x dx. So this is integral from 0 to 1. 1 minus x by 2 will just divide by x plus x squared by 3 minus x4 by 4 and so on. Now we can just integrate this part by part, and that's easier. We can all do that. So that is just x minus x squared by 2 square plus x cubed by 3 square minus x to the power sorry, I guess I missed this is x cube, x square, so this will be x cube. Yeah, so this is x4 by 4 square and so on, evaluated from 0 to 1. So now after this, we can just evaluate the integrals at the limits 0 and 1. So this will give us 1 minus this 2 square, yeah, x square by 2 square, okay. So 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square and so on. And when evaluated at 0, these will just all of them be 0 since we have x in them, so minus of 0. So now what we have is we just have to evaluate this integral. Yeah. Now for to evaluate this integral, first we know that this is just a converging sum. Since this is just an alternating series of the famous zeta of 2, yeah, this is just and I equals to we don't have this 1 over here. I mean this is 2 square here. Okay, so this is 2 square. Now this is just from I equals to 1 to infinity, 1 by I square times minus 1 to the power n over here, n plus 1 over here. So this is just an alternating series of I equals to 1 to infinity 1 over I square. And since this series converges, the alternating series will also converge. Yeah. And now, since we know that this series converges, we would want to find its value. For that, since this is a converging series, we can make the manipulations. So we will make some manipulations and try to find its value. Now, for this one, Firstly, we should also know that the zeta of the 2, the sum of this series 1 by y square, this is famous Euler sum, and this is equals to pi square by 6. Yeah, so if we know this, we are perfectly ready to evaluate this one. So for this one, what we can make is, we can make this given change. We can first add 1 by 2 square, also add 1 by 4 square, and so on, and then subtract 2 times 1 by 2 square, yeah, 1 by 4 square. So this just doesn't hamper our series. The series is just the original. We have just made some manipulations. Okay, and now after we have this, this is just equals to original series. Now we don't know that this sum is just pi square by 6 and minus 2, and if we just take out 1 by 4 common from all these terms, we have 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square, and so on. Now again we know that this is just pi square by 6, so this is pi square by 6 minus 1 by 2 times pi square by 6, so that will be pi square by 12. So we have got the value of sum of this series, alternating series, and it's actually equals to pi square by 12. So now this is our answer. So pi square by 12 is also our answer, and yeah, pi square by 12 is the answer. And I hope you enjoyed and learned how we evaluate integrals with series. Thanks for watching. I hope we had a good time ahead.